Every second, the universe is expanding, pulling galaxies farther apart, stretching the very fabric of space. But here's the mind-bending question no one can fully answer. What lies beyond it all? Is there an invisible boundary, a multiverse waiting just outside our reach, or is it expanding into absolutely nothing? Think about it. If galaxies are being pushed apart every second, there has to be something they're expanding into, right? Or could it be that our entire idea of space is completely wrong? This mystery could change everything we know about reality. Today we're diving into one of the biggest mysteries in science. We've all heard about the expansion of the universe, but here's the mind-bending part. It's not just galaxies drifting apart. Space itself is stretching. That means everything, from galaxies down to the very fabric of space, is expanding. But what is this space expanding into? Is there anything outside it, or is space just infinite? Today, we're diving into these profound questions to understand what scientists have uncovered so far and what remains hidden in the cosmic unknown. For thousands of years, humans viewed the universe as a fixed and unchanging space, where stars and galaxies remained in their places like permanent fixtures in the sky. This belief provided a sense of comfort, making the vast cosmos feel familiar and stable. However, in the 20th century, astronomers made a revolutionary discovery that changed everything. They observed that galaxies are not just standing still, they are actually moving away from us. The surprising part is that the farther away a galaxy is, the faster it seems to be receding. This finding suggested that the universe is expanding, prompting a profound question. If the universe is expanding, what is it expanding into? This question stirs the imagination and invites us to think deeply. Is there a vast emptiness beyond the universe, where it stretches out into nothingness? Or could it be that the universe is expanding within a larger space that we don't fully understand yet? As we ponder these ideas, we encounter fascinating theories about multiple dimensions and even the possibility of other universes existing alongside our own. Understanding what lies beyond the observable universe opens up a world of possibilities and challenges our perceptions of reality. It pushes us to explore the nature of space, time, and the very fabric of existence. So what does it really mean for the universe to expand? Are we missing a key piece of the puzzle? Or could it be that reality itself operates on a level we're just beginning to understand? Let's start with Edwin Hubble, the American astronomer who changed everything. Back in the 1920s, Hubble observed something that would turn the world of astronomy upside down. He found that the light coming from distant galaxies was redshifted, meaning it shifted towards the red part of the spectrum. This redshift indicated that galaxies weren't just stationary, they were moving away from us. Not only that, but Hubble noticed a pattern. The farther a galaxy was, the faster it seemed to be moving away. This discovery led to what's now called Hubble's law, which essentially states that the universe is expanding. Imagine blowing up a balloon with tiny dots on it. As the balloon inflates, the dots move farther apart, not because they're moving on their own, but because the surface of the balloon is expanding. Now, apply that to the universe. But instead of dots on a balloon's surface, we have galaxies, and instead of just expanding in 2 dimensions, it's happening in 3-dimensional space. The galaxies aren't flying through space away from each other. Rather, space itself is expanding and carrying them along for the ride. But here's where it gets mind-boggling. What is this space expanding into? One possible answer is that space might be infinite, with no boundary and no edge. In this case, expansion doesn't mean pushing into something else. It simply means the distances between objects within the universe are increasing. There's no outside because the universe has no edge, it just keeps going. Some scientists, however, think the universe might be finite, but unbounded. Imagine the surface of the Earth. You can travel around it forever without hitting an edge, yet the Earth's surface area is finite. If the universe is like this, you could theoretically travel in one direction and eventually return to your starting point, even though there's no boundary. In this model, the universe wouldn't expand into anything, it's simply growing within itself. Now let's turn our attention to a mysterious force known as dark energy. This force, which scientists discovered in the 1990s, is causing the universe not only to expand, but to accelerate in its expansion. Initially, scientists thought that gravity would eventually slow the expansion down, perhaps even causing the universe to collapse back on itself. But when they studied distant supernova, explosions of massive stars, they found that the universe's expansion was actually speeding up. So what exactly is dark energy? That's one of the biggest questions in modern cosmology. Right now, dark energy makes up about 70% of the universe, yet we can't see it or measure it directly. All we know is that it's acting like a kind of anti-gravity, pushing everything apart. This means that if the expansion continues accelerating, distant galaxies will eventually recede so quickly that their light will never reach us. Our observable universe will shrink, leaving us in an increasingly lonely cosmos. What about the concept of a multiverse? Some physicists propose that our universe might be just one of many, part of a vast multiverse, where countless other universes exist, each with its own unique properties. In this theory, our universe's expansion could be pushing into other universes, creating a boundary between ours and these other unseen worlds. However, this idea remains highly speculative, and we currently have no way to observe or test the existence of other universes. Then there's the idea of cosmic inflation. Right after the Big Bang, the universe experienced an unbelievably rapid expansion called inflation. During this brief moment, the universe expanded faster than the speed of light, growing from a minuscule point to something vast and smooth. This inflationary period not only set the stage for the universe as we know it, but also hints at the idea that space itself can expand without needing anything to expand into. In other words, the expansion doesn't require an external container. As we delve deeper into these fascinating concepts, we begin to uncover the intricate theories that attempt to explain the nature of our expanding universe and the forces at play. For instance, scientists are continuously researching the nature of dark energy, seeking to understand its properties and how it influences the universe's fate. The relationship between dark energy and the rate of expansion raises questions about the ultimate destiny of the cosmos. Will it continue to expand forever, or will it eventually reach a point of equilibrium? Additionally, the idea of a multiverse invites us to explore the possibility that our universe is just one piece of a much larger puzzle, where other realities exist parallel to ours. Meanwhile, the theory of cosmic inflation reshapes our understanding of the universe's beginnings, suggesting that the very fabric of space can expand independently of physical boundaries. By examining these theories and their implications, we inch closer to answering the profound question of what the universe is expanding into and what mysteries lie beyond our current understanding. The balloon analogy, but with a twist. Imagine you're looking up at the night sky. You see stars and galaxies scattered across the vast darkness, all seemingly fixed in place. But what if I told you that everything you see up there, every star, planet, and galaxy, is constantly moving further away from each other, stretching out across the universe? And it's not just the objects themselves moving apart. It's space itself that's stretching, expanding with them. To help make sense of this, scientists use a very famous analogy. They compare the universe to the surface of a balloon. Imagine a balloon that hasn't been inflated yet. Now, picture drawing small dots on its surface, each dot representing a galaxy. Now start blowing air into the balloon, and as it expands, you'll see that the dots move farther apart. The balloon's surface stretches, so every dot moves away from every other dot. This is very much like our expanding universe. The dots represent galaxies, and as space itself stretches, these galaxies move apart. Importantly, just as there's no center on the balloon's surface, scientists believe there's no central point in the universe where the expansion began. Instead, every point in the universe is expanding away from every other point. Now, you might think that if you're expanding the surface of a balloon, it's obviously growing into the air around it. But in our universe, there isn't any surrounding space for it to expand into. According to current scientific understanding, there is no outside of our universe. Imagine that the balloon's surface is all there is. There's no inside and no outside, only the surface itself. Doesn't that mean we're saying space can grow without expanding into anything else? It sounds impossible, right? Our brains are used to thinking in terms of things having an outside, but the universe doesn't follow this rule. The space between galaxies stretches and distances grow, but there's no need for the universe to be expanding into anything. It just expands within itself, which is a concept that boggles the mind. The balloon analogy is helpful because it gives us a way to picture how every part of space expands equally, with galaxies moving apart as space stretches. But it's also misleading in one major way. It suggests that the universe has an outside. And while this is true for our balloon, it's not the case for the universe. To understand why, let's talk a little bit about dimensions. Our brains are trained to think in 3 dimensions. We can go forward and back, left and right, up and down. The balloon, however, has only 2 dimensions on its surface, so we need to add an extra layer of imagination. Think of it this way. The universe might be expanding in a way that our 3-dimensional minds simply aren't built to fully comprehend. But even though we can't see the whole picture, the balloon analogy still helps us understand one core truth. The universe doesn't expand from any single point. If you were a tiny creature living on the surface of that balloon, you wouldn't know anything about an inside or outside of the balloon. You just know that everything around you is moving away, like a cosmic game of musical chairs that never stops. Now, let's think about the actual scale of the universe we're talking about here. Imagine if that balloon were billions and billions of times bigger than we could ever imagine. Our observable universe, the part we can see, is already around 93 billion light-years across. That means light, which travels at about 300,000 kilometers per second, has taken billions of years just to reach us from the farthest galaxies we can observe. But the universe is much, much larger than what we can see. In fact, many scientists believe it could be infinite. If that's the case, then the analogy of the balloon becomes even more abstract. The balloon analogy assumes we're dealing with something finite, but if the universe is infinite, it has no surface to expand in the first place. It just is expanding everywhere, in all directions, with no limit. Another point we need to address is that expanding space doesn't mean galaxies are moving through space in the way we might imagine. When we see a car driving down the road, we know it's moving from point A to point B. But galaxies in the universe aren't actually moving in this way. Instead, it's the space between them that's stretching. Imagine you and a friend are standing on opposite sides of a trampoline. As the trampoline stretches, you move further apart, even though neither of you are actually walking anywhere. The distance between you increases because the material underneath you is expanding. In the same way, galaxies appear to be moving away from each other, but they're not traveling through space. The fabric of space itself is stretching, carrying the galaxies with it. This is a key difference from how we usually think about motion. In fact, some galaxies are moving apart so quickly that they're already beyond the reach of light. They're moving away faster than the speed of light itself, so their light will never reach us. One of the ways scientists know the universe is expanding is by looking at something called redshift. When astronomers look at light coming from distant galaxies, they see that it's shifted towards the red end of the spectrum. This redshift happens because as space expands, it stretches the light waves traveling through it. The longer the wavelength, the redder the light appears. So when we see redshifted light, we know that the galaxy emitting it is moving away from us. The redshift of light from galaxies was one of the earliest pieces of evidence that the universe is expanding. In the 1920s, astronomer Edwin Hubble observed that galaxies farther away from us were moving faster than galaxies closer to us, a discovery that led to what's now known as Hubble's law. This law showed that the farther away a galaxy is, the faster it's receding, supporting the idea of an expanding universe. Now that we understand the basics of expansion, let's add one more layer: dark energy. Dark energy is a mysterious force that seems to be pushing galaxies apart at an ever-increasing rate. If you go back to our balloon analogy, imagine that not only are you blowing air into the balloon, but you're also somehow speeding up the inflation, making it expand faster and faster with each passing second. Scientists believe dark energy makes up about 70% of the universe, yet we know almost nothing about it. It seems to act like a kind of anti-gravity, pulling things apart instead of drawing them together. This accelerating expansion caused by dark energy means that over time, distant galaxies will drift further and further apart until they're beyond the reach of our telescopes. Eventually, if this continues, we might only be able to see a handful of galaxies in our own neighborhood, with everything else lost beyond the horizon. As helpful as the balloon analogy is, it's also limited. It's hard to truly imagine a universe expanding without any outside space. It's even harder to picture a universe where space itself stretches, carrying galaxies along without them actually moving. But perhaps the real twist in the balloon analogy is that it's meant to show us that our understanding of space might be fundamentally flawed. In the balloon analogy, we only have the surface to work with. There's no inside or outside, and that's just the way it is. But in our universe, we're used to 3 dimensions: width, height, and depth. Imagining a 3-dimensional space that behaves like a balloon surface is almost impossible, and yet that's exactly what scientists ask us to do. Understanding the expansion of the universe isn't just an exercise in imagination, it has real implications for how we view reality itself. If the universe can expand without expanding into anything, it challenges the very way we think about existence. And as we learn more about dark energy and the forces shaping our universe, we may come to understand that the universe's expansion and the space it's made of are even stranger than we ever imagined. Does the universe have an edge? Let's dive deeper into the strange idea of whether the universe has an edge or a boundary. Our everyday experiences make us think everything must have some kind of edge, like a wall, a fence, or a border. But the universe doesn't play by the same rules we're used to on Earth. When we talk about the universe, things start to get complicated, especially because scientists don't think it has any kind of physical boundary. So if you could travel in a straight line across the universe, could you reach the end of it? The answer, as strange as it sounds, is no. As far as we can tell, the universe has no edge or border that you could cross. One way to picture this is to imagine Earth. If you were to walk in a straight line around the Earth, you would eventually return to the exact spot you started. At no point would you fall off an edge of the Earth, because the Earth is curved. It loops back on itself, so you could keep going forever in one direction without ever reaching an end. The universe, in a way, might work similarly. Many scientists think space could be curved in such a way that if you traveled in a straight line across it, you'd eventually end up back where you started, just like walking around Earth. But here's where things get even stranger. Unlike the Earth, which is round and finite, the universe could be either finite or infinite, and we're not sure which one. If the universe is finite, it might wrap around itself in a loop, just like Earth. But it would be a 3-dimensional loop, which is incredibly hard to imagine. If it's infinite, then it just keeps going forever, with no end or border at all. But either way, you wouldn't hit any kind of edge, wall, or boundary. There would be no line you could cross to suddenly be outside the universe. This idea is difficult to accept because our brains are used to thinking of everything as having a container or boundary. We think of the universe as a giant thing that needs to exist somewhere. But scientists tell us that space doesn't need anything to be inside of. The universe just exists, and it stretches out in all directions without needing an edge or an outside space to expand into. If space is infinite, there's no limit. If it's finite, it loops back on itself, so it doesn't require a border. What makes this concept even more fascinating is the fact that we can only observe a small portion of the universe, the part we call the observable universe. This is the region from which light has had enough time to reach us since the beginning of the universe. Imagine standing in the middle of a foggy field where you can only see a certain distance in any direction. Everything beyond that distance is hidden from view. In the universe, the observable limit is set by the speed of light and the age of the universe, which means we're only able to see objects that are within roughly 93 billion light years. Anything beyond that is simply too far away for its light to have reached us yet. The observable universe is like a bubble, but it's not a true boundary or edge. It's just the farthest distance we can see right now. Beyond that bubble, the universe likely continues, possibly endlessly. Scientists believe that what we can see is only a tiny fraction of the entire universe, and that beyond the observable universe, there's much, much more. Maybe even an infinite amount of space and galaxies that we'll never be able to observe because they're simply too far away. The concept of an edge is further complicated by the idea that the universe might not just loop back on itself in space, but also in time. If you were able to look far enough into the distance, you wouldn't just be looking across vast stretches of space. You'd also be looking back in time. Light from distant galaxies takes millions or even billions of years to reach us. So when we look at a far-off galaxy, we're seeing it as it was billions of years ago. This means that if we could somehow see far enough, we might actually be able to see the early moments of the universe itself. The farther we look, the closer we get to the beginning of everything. What's even more puzzling is the question of what lies beyond the observable universe. Since we can't see beyond a certain distance, we have no way of knowing if the universe beyond looks similar to what we can see, or if it might be vastly different. Scientists assume that the universe is uniform, meaning it's generally the same everywhere on large scales, based on the principle of cosmological homogeneity. This principle suggests that if we could somehow see past our observable universe, we would likely find more of the same. More galaxies, more stars, more cosmic structures stretching out as far as space allows. But there's always a possibility that the universe beyond our reach could be different. Maybe there are regions with more matter, fewer galaxies, or areas with physical laws that don't quite match what we experience in our part of the cosmos. It's also possible that beyond the observable universe, space might become even stranger, maybe containing phenomena we haven't even begun to imagine. This idea leads to a more speculative concept, the multiverse. Some scientists believe that what lies beyond our observable universe might not just be more of the same, but entirely separate universes, each with its own set of physical laws and properties. According to this theory, our universe could be one bubble in a vast multiverse of other universes, each one self-contained and possibly with different dimensions, forces, or even types of matter. If this is true, then our observable universe is just one tiny part of a much larger reality, one that contains countless other universes that we'll never see or interact with. One theory, called cosmic inflation, suggests that right after the Big Bang, the universe expanded incredibly quickly, creating regions of space that would never interact with each other. Some cosmologists think that this rapid inflation might have created multiple bubble universes, each one isolated from the others. If this is true, then our universe isn't expanding into nothing, but rather exists alongside countless other universes, each expanding within its own bubble of space-time. The concept of dark energy also adds another layer to this mystery. Dark energy is the strange force that seems to be pushing the universe to expand faster and faster. Imagine that not only is space expanding, but this expansion is accelerating. If we go back to the balloon analogy, it's like blowing up the balloon faster and faster, making it expand more quickly over time. Dark energy makes up roughly 70% of the universe, but we don't know what it actually is. It seems to act as a kind of anti-gravity, pushing things apart instead of pulling them together. The presence of dark energy suggests that our observable universe will keep expanding indefinitely, with galaxies moving farther and farther away from each other. Over time, more and more galaxies will cross beyond the edge of our observable bubble, vanishing from our view forever. The universe might continue to expand so rapidly that only a few nearby galaxies will remain visible to us, with everything else receding into darkness. This means that even if the universe has no true edge or boundary, our view of it will become increasingly limited as time goes on. In the end, we're left with the strange realization that the universe might have no edge, no boundary, and no outside. It could simply be an endless stretch of space and time, expanding within itself. Whether it's finite or infinite, whether it's one of many universes or completely unique, remains a mystery. We may never know exactly what lies beyond the universe we can observe, but one thing is clear: our understanding of space and boundaries may need to be completely redefined to comprehend the true nature of the cosmos. The observable universe and beyond. The universe is a vast and complex entity, filled with mysteries that challenge our understanding of reality. One of the most intriguing aspects of the universe is the concept of the observable universe. This term refers to the portion of the universe that we can see, or more accurately, the portion from which light has had time to reach us since the universe began. This limited view is shaped by the age of the universe, which scientists estimate to be about 13.8 billion years. Thus, the observable universe is bounded by the distance light has traveled during that time, creating a sort of cosmic horizon. Imagine standing in a foggy field where visibility is limited. You can see only as far as the fog allows. In the same way, we stand at the center of our own observable universe, peering into the darkness beyond. When we look out into space, we see a tapestry woven from stars, galaxies, and cosmic phenomena. The observable universe is vast, containing an estimated 2 trillion galaxies, each with billions of stars. The sheer size of this observable section is awe-inspiring, but it is crucial to understand that it represents only a fraction of the entire universe. The actual universe may extend far beyond what we can observe, possibly infinitely so. This idea challenges our comprehension of space and time, suggesting that the universe does not merely stretch into something else outside our reach, but rather expands within itself. To grasp this concept, let's delve into what it means for the universe to be expanding. The expansion of the universe is a phenomenon that was first observed in the early 20th century when astronomer Edwin Hubble discovered that galaxies are moving away from us. This observation led to the formulation of Hubble's law, which states that the farther away a galaxy is, the faster it appears to be receding. This suggests that the universe itself is stretching, as if it were a balloon being inflated, with galaxies moving away from each other as space itself expands. But if the universe is expanding, what is it expanding into? This question is at the heart of a fascinating paradox. We often think of expansion as something that requires additional space to grow into. For example, when you blow up a balloon, the rubber expands into the surrounding air. However, in the case of the universe, it is not expanding into any external space. Instead, it is more accurate to say that space itself is increasing. This means that distances between galaxies are growing, while the space between them expands. Consider this. If you were to take a piece of paper and draw dots on it to represent galaxies, as you stretch the paper, the dots would move farther apart from each other. The paper represents the fabric of space, and as it expands, the galaxies move away from each other. However, there is no edge of the paper where it meets an outside. The universe operates in a similar way, expanding without a boundary or external environment. Understanding the observable universe helps contextualize this concept. Since we can only see light that has had time to reach us, our observable universe is limited to a spherical volume centered around us. This sphere has a radius of about 46.5 billion light-years, which accounts for the expansion of space over time. Beyond this sphere lies the unobservable universe, which may contain an infinite number of galaxies and structures we can only speculate about. This unobservable portion is a reminder that our current understanding is merely a glimpse into a much grander reality. As we consider the implications of an expanding universe, we encounter another layer of complexity: the nature of cosmic inflation. This theory posits that the universe underwent a rapid expansion in its earliest moments, much faster than the speed of light. During this inflationary period, the universe grew exponentially, setting the stage for the formation of galaxies, stars, and all structures we observe today. It suggests that even in the earliest moments, the universe was not just expanding into empty space, but was fundamentally altering the nature of space itself. The concept of the universe being potentially infinite raises profound questions about its structure. If the universe is infinite, then it means that space is unbounded. When we talk about the universe expanding, we are essentially acknowledging that distances are increasing, while also recognizing that the cosmos may extend infinitely in every direction. This leads to a thought-provoking consideration. If the universe is infinite and ever-expanding, does that imply there are regions of space where conditions may repeat, creating duplicate versions of galaxies, stars, or even planets? The answer to this question hinges on our understanding of probability and the nature of infinity. One of the most mind-boggling consequences of an infinite universe is the idea of cosmic topology. Our universe could be shaped in ways that defy our conventional understanding of geometry. For instance, if the universe is finite but unbounded, it could curve back on itself, creating a scenario where traveling in a straight line could eventually bring you back to your starting point. In this model, the universe is like a three-dimensional sphere in which the surface has no edges. Alternatively, if the universe is truly infinite, then the possibilities are endless, with no defined boundaries or edges. This exploration of cosmic expansion and the nature of the universe poses philosophical questions as well. The concept of an infinite universe challenges our understanding of existence and our place within it. It invites us to ponder the significance of life in a cosmos that may be vast beyond measure, filled with mysteries yet to be discovered. The more we learn about the universe, the more we realize how much remains unknown. Moreover, this journey into the nature of the cosmos intersects with the fields of philosophy, theology, and even psychology. How do we, as conscious beings, reconcile our finite lives with the vastness of an infinite universe? What does it mean for us to seek understanding and knowledge within such a grand and enigmatic setting? In conclusion, the observable universe is just the tip of the iceberg in our quest to comprehend the cosmos. While we can only perceive a fraction of the universe, the notion of an expanding universe presents both thrilling possibilities and deep uncertainties. As we continue to study the universe, we are drawn into a narrative that transcends the boundaries of science, beckoning us to explore not just the physical properties of space, but also our place within this extraordinary tapestry of existence. The universe expands, but it does so in a way that challenges our perception of reality, encouraging us to look beyond the veil of the observable and to ponder the infinite mysteries that lie beyond. The role of cosmic inflation and the Big Bang. To understand the profound nature of cosmic expansion, we must delve deep into the origins of our universe, beginning with the moment known as the Big Bang. This event marks the inception of everything we know: space, time, matter, and energy. The Big Bang is not just an explosion, but a monumental event that set the stage for the universe as we perceive it today. It was a time when all the energy and matter we can see were compressed into an infinitesimal point, a singularity where the laws of physics as we know them began to take form. The initial conditions of the universe following the Big Bang were extreme and chaotic. In the first moments, the universe was incredibly hot and dense, filled with particles racing around at unimaginable speeds. But within a fraction of a second, something extraordinary happened: cosmic inflation. This rapid expansion transformed the universe from a state smaller than an atom into a vast expanse stretching across light years. Imagine blowing up a balloon so quickly that the rubber stretches evenly, creating a smooth and uniform surface. This is similar to how inflation worked, smoothing out the cosmos and laying the groundwork for the structure we observe today. During this inflationary period, the universe expanded exponentially, increasing in size by a factor of at least 10^26 in a mere 10^36 seconds. This astonishing rate of growth means that the universe transformed from an unrecognizable state into a vast and complex environment. However, this rapid expansion also gives rise to critical questions about what existed before this event and what, if anything, the universe expanded into. The questions surrounding the beginnings of the universe can lead us into deep philosophical territory. If the universe was born from the Big Bang, what was there before it? Conventional thinking might suggest that if something expands, it must have a surrounding space to expand into. Yet, as we probe deeper, we encounter a striking conclusion that many scientists have posited. There was no before the Big Bang in any conventional sense. The Big Bang did not merely create matter and energy, it also gave rise to time and space themselves. Before the Big Bang, asking what existed is somewhat of a misnomer. In this context, there was no space to contain anything, and thus there was no before to speak of. Imagine a blank canvas that has not yet been touched by a paintbrush. The absence of any form or structure defines its existence. But the nothingness we're discussing here goes beyond mere absence. It is not a void filled with potential. It is an absence of even the concept of void. It's difficult for us to fathom because all our experiences are rooted in a universe filled with time and space. To wrap our minds around this concept, we must consider the implications of a universe that began as a singularity. At this point, all the laws of physics, as we understand them today, break down. Quantum mechanics and general relativity, the two pillars of modern physics, give us glimpses into the behavior of particles and the curvature of space-time, respectively. However, at the singularity, these two theories collide, and our current understanding fails to provide answers. It raises the question of whether a new theory, perhaps one that integrates quantum mechanics and gravity, could explain the very origins of the universe. Another intriguing aspect of cosmic inflation is how it explains the uniformity of the universe. After inflation, the universe became incredibly homogeneous and isotropic, meaning it looked the same in all directions on a large scale. This is evidenced by the cosmic microwave background radiation, which fills the universe and is remarkably uniform in temperature. The slight variations we observe in this background radiation are the seeds of galaxies and large-scale structures that formed later in the universe's evolution. The inflationary model also helps to explain why we observe such a smooth universe, devoid of the expected irregularities that would result from a more chaotic initial state. Inflation stretched out any initial irregularities, smoothing them over and creating the conditions necessary for the formation of galaxies. It sets the stage for a universe where galaxies are not just scattered randomly, but are organized into clusters and superclusters, governed by the gravitational forces that shaped them over billions of years. However, the questions do not end with the initial conditions of the universe. The role of cosmic inflation suggests that the Big Bang may not have been a one-time event, but rather part of a larger, more complex cosmic landscape. Some theories posit the existence of a multiverse, where our universe is just one of many that emerged from different inflationary processes. Each universe could have different physical laws, constants, and properties, further complicating our understanding of existence. If this idea holds, it challenges the uniqueness of our universe and the very nature of reality itself. The implications of an expanding universe, coupled with the framework provided by cosmic inflation, force us to reconsider our place in the cosmos. We often think of ourselves as occupying a central position in a universe that exists around us. Yet, as we learn more, it becomes apparent that our universe is but a small part of a potentially vast multiverse, with many other realms existing beyond our perception. This realization can be both humbling and exhilarating, as it opens up a new frontier of inquiry and imagination. In contemplating the nature of the universe, we are also led to consider the philosophical implications of existence. If time and space were born from the Big Bang, how do we understand concepts like cause and effect, or beginning and end? In our daily lives, we operate under the assumption that every effect has a cause, but at the very beginning of everything, the rules seem to change dramatically. As scientists continue to explore the frontiers of cosmology, the quest to understand the universe's origins pushes the boundaries of our understanding. Researchers use powerful telescopes to gaze into the distant cosmos, seeking evidence that might illuminate our understanding of the Big Bang and cosmic inflation. They look for patterns in the cosmic microwave background radiation and study the large-scale structure of the universe to gather clues about its formative moments. Moreover, advancements in particle physics, particularly through experiments conducted at facilities like the Large Hadron Collider, may one day offer insights into the conditions of the early universe. These experiments seek to recreate conditions similar to those present in the first moments after the Big Bang, allowing scientists to explore fundamental questions about matter, energy, and the forces that govern our universe. As we stand on the precipice of understanding, the mysteries of the universe beckon us. The concept of cosmic inflation and the Big Bang is not merely an academic exercise. It profoundly impacts our understanding of reality, existence, and our place in the cosmos. Each discovery raises new questions and opens new avenues of inquiry. The universe, in its majestic complexity, invites us to explore and ponder the nature of everything that exists. In conclusion, the role of cosmic inflation and the Big Bang is pivotal in our understanding of the universe's expansion. This narrative, woven with threads of scientific discovery and philosophical inquiry, illustrates a journey that spans the vast expanse of time and space. The Big Bang created not only the matter and energy we observe, but also the very framework of time and space. As we explore these concepts, we find ourselves part of a larger story, a story that is still unfolding and will continue to inspire generations of scientists, philosophers, and dreamers. In the grand tapestry of existence, the questions we ask are just as significant as the answers we seek, guiding us toward deeper understanding and connection with the cosmos that surrounds us. Is space finite or infinite? The question of whether space is finite or infinite is one of the most profound and intriguing inquiries in cosmology and philosophy. To grapple with this concept, we must consider what we mean by space and the implications of its potential finiteness or infiniteness. If space is infinite, it would extend endlessly in all directions, without any boundaries or edges. On the other hand, if space is finite, it would have a specific size or volume, though it may not necessarily have a clear boundary or edge. To visualize these two possibilities, let's think about familiar analogies. Imagine a flat sheet of paper. This is a finite space with a clear edge. If you were to walk to the edge of the paper, you would reach a boundary, which marks the limit of that surface. Now consider a sphere, like the surface of a basketball. If you were to walk along the surface of the ball, you could continue indefinitely without ever encountering an edge. Instead, you would eventually return to your starting point. This is an example of a finite space without a boundary. This idea of a finite universe that wraps around itself can be perplexing. For instance, some scientists propose that our universe could be shaped like a three-dimensional version of a two-dimensional surface, such as a torus, the shape of a donut. If you were to travel far enough in one direction, you would eventually find yourself back where you started, suggesting a universe that is both finite and unbounded. This concept defies our typical understanding of boundaries and edges, as it emphasizes the idea of continuity and connectedness within a closed system. Another way to conceptualize this notion is through the lens of video games. In many video game worlds, players can explore a defined map. When a player walks off one side, they may reappear on the opposite side without any awareness of having crossed an edge. This experience reflects a finite universe. The game world has a set size, but the player does not encounter a boundary or an end. Instead, the world loops back on itself, creating an illusion of infinity within a finite space. This analogy captures how our universe might function, where one could traverse the cosmos without ever hitting a physical boundary. In terms of scientific inquiry, the question of whether space is finite or infinite is intertwined with our understanding of the universe's shape and structure. The curvature of space plays a crucial role in this discussion. General relativity tells us that massive objects like planets and stars warp the fabric of space-time around them. This curvature can lead to different possible geometries for the universe: flat, open, or closed. A flat universe is described as having zero curvature, much like a sheet of paper that extends infinitely in all directions. An open universe has negative curvature, resembling a hyperbolic surface that expands forever, while a closed universe has positive curvature, similar to the surface of a sphere. Current observations, particularly from the cosmic microwave background radiation, suggest that the universe is flat on large scales, but this does not rule out the possibility of it being finite. One fascinating aspect of cosmic topology is that our universe could still be finite even if it appears flat on large scales. For example, if the universe is shaped like a torus, it could be flat yet finite, as mentioned earlier. This leads to intriguing implications for cosmology. If you were to travel far enough in one direction, you might eventually find yourself returning to your original location, experiencing the cosmos as both finite and infinite. The concept of cosmic inflation adds another layer of complexity to this discussion. During the rapid expansion of the universe in its earliest moments, inflation smoothed out the distribution of matter and energy, creating a homogeneous and isotropic cosmos. This inflationary period could lead to a universe that is extremely large, possibly even infinite in extent, but still exhibits localized regions that appear finite to observers like us. As we consider these ideas, it is essential to recognize that our observations of the universe are inherently limited. The observable universe, the portion of the universe from which light has had time to reach us, is about 93 billion light-years in diameter. However, beyond this observable horizon, the universe may extend far beyond what we can see. Whether that unobservable universe is finite or infinite remains an open question, one that scientists continue to investigate through theoretical models and observations. To further illustrate the concept of finite versus infinite space, we can turn to the idea of multidimensional space. In higher dimensional theories, such as string theory, space may possess more dimensions than the three we commonly experience. Some theorists propose that these extra dimensions could be compactified or curled up in such a way that they create a finite space while allowing for infinite paths of movement within that space. This notion challenges our conventional understanding of space and invites us to consider the existence of realms beyond our immediate perception. The implications of a finite or infinite universe extend beyond mere academic curiosity. They touch upon the very nature of existence and the boundaries of our understanding. If the universe is infinite, it suggests that there are infinitely many possibilities, potentially leading to the existence of other regions or universes with different physical laws and structures. This idea, known as the multiverse hypothesis, posits that our universe is just one of many, each with its own unique characteristics. The philosophical ramifications of an infinite universe are profound. It prompts us to question our place in the cosmos and our understanding of reality itself. In an infinite universe, the idea of uniqueness becomes blurred, as every event, object, or phenomenon may have countless variations scattered throughout space. This perspective challenges the notion of individuality and can evoke feelings of both insignificance and wonder. Conversely, if the universe is finite, it invites us to ponder the implications of limits and boundaries. A finite universe implies that there is a specific size and scope to reality, and this raises questions about what lies beyond that boundary, if anything. It also suggests that our understanding of the universe must account for a tangible, measurable cosmos, pushing the boundaries of scientific inquiry and exploration. As we continue to explore the nature of space, we find ourselves at the intersection of science, philosophy, and even spirituality. Questions about the infinite and the finite resonate with fundamental human inquiries about existence, purpose, and the nature of the cosmos. The pursuit of knowledge about the universe is not merely an intellectual exercise. It is a journey that leads us to confront the mysteries of life and our place within it. In recent years, advances in observational technology, such as powerful telescopes and deep space probes, have enabled scientists to probe the farthest reaches of the universe. These tools help us gather data that can shed light on the universe's structure, composition, and potential finiteness or infiniteness. However, as we make these discoveries, we must also confront the inherent limitations of our observations. The vast distances involved and the finite speed of light mean that we can only glimpse a portion of the universe, leading to inherent uncertainties about its true nature. In conclusion, the question of whether space is finite or infinite is a rich and complex topic that invites exploration on multiple levels. Whether the universe is an infinite expanse without boundaries or a finite realm with a unique structure, the implications of either scenario are profound. This inquiry encourages us to engage with the cosmos, contemplating our existence and place within a reality that is vast beyond measure. As we journey through the universe, we are reminded that the quest for understanding is as significant as the answers we seek, driving us to explore the depths of knowledge and the mysteries that lie ahead. The exploration of space, its limits, and its boundless possibilities is a testament to the enduring human spirit and our relentless pursuit of truth. What about parallel universes? The notion of parallel universes, often collectively referred to as the multiverse, presents one of the most fascinating and bewildering concepts in modern cosmology and theoretical physics. It challenges our understanding of reality by suggesting that there may exist not just one universe, but a vast multitude of universes. each potentially governed by its own unique set of physical laws and constants. This idea opens up a realm of possibilities that extend far beyond the boundaries of our observable universe, prompting questions about the nature of existence itself. To grasp the concept of the multiverse, we can begin by envisioning our universe as a single bubble in a vast cosmic foam. Each bubble represents a separate universe with its own properties and characteristics. Some bubbles may resemble our own universe closely, while others could be radically different, featuring entirely distinct physical laws, dimensions, or even forms of matter and energy. This visualization helps to illustrate the complexity and diversity that could exist beyond our perception. The origins of the multiverse theory can be traced back to various branches of theoretical physics, including quantum mechanics, cosmology, and string theory. Each of these fields offers different insights into the nature of reality and the potential existence of parallel universes. In quantum mechanics, for instance, the idea of superposition suggests that particles can exist in multiple states simultaneously until measured. This has led to interpretations, such as the many worlds interpretation, which posits that every quantum event spawns a branching of universes. In this view, every decision, every random event, creates a new universe where every possible outcome occurs. This concept invites us to imagine an infinite number of parallel realities coexisting alongside our own. In one universe, you might have made a different choice at a pivotal moment in your life, leading to a radically different outcome. In another universe, the very laws of physics could be altered, resulting in entirely different structures, forms of life, or even the absence of certain fundamental forces. The sheer vastness of these possibilities stretches the limits of our imagination and challenges our understanding of identity, causality, and existence. In cosmology, the multiverse theory gains traction through the framework of cosmic inflation. During the rapid expansion of the universe in its infancy, different regions could undergo their own inflationary processes, leading to the creation of distinct bubble universes. This scenario proposes that our universe is just one of many that were born from the same inflationary event, with each bubble expanding independently, leading to a diverse tapestry of universes. In this context, the multiverse can be seen as a consequence of the underlying mechanisms driving cosmic inflation, where different regions of space-time evolve according to their own unique histories. String theory, a theoretical framework that seeks to reconcile quantum mechanics and general relativity, also supports the idea of the multiverse. In string theory, the fundamental building blocks of the universe are not point-like particles, but rather tiny vibrating strings. The way these strings vibrate determines the properties of particles and forces. String theory suggests that there are many possible configurations of strings, leading to a landscape of potential universes, each with its own distinct physical laws and characteristics. In this landscape, some configurations may lead to stable, life-supporting universes like ours, while others may be unstable or inhospitable. Despite the theoretical foundations of the multiverse, the idea raises profound philosophical and scientific questions. One of the primary challenges is the difficulty of testing or observing other universes. Since they may exist outside the observable universe, we may never have the means to interact with or gather empirical evidence for their existence. This limitation leads to debates about the scientific validity of the multiverse theory. Some argue that it is unfalsifiable and therefore not a proper scientific hypothesis. However, proponents maintain that the multiverse emerges naturally from well-established theories in physics, suggesting that it could provide a more comprehensive understanding of the cosmos. The implications of the multiverse theory extend beyond physics and cosmology into the realms of philosophy and existential inquiry. If multiple universes exist, each with its own laws and properties, it raises questions about the nature of reality and our place within it. Are we merely one version of a multitude of selves, living out different lives in parallel universes? How does the existence of alternate realities influence our understanding of choice, fate, and free will? The multiverse invites us to reconsider the foundations of our beliefs and our understanding of identity. Furthermore, the multiverse concept can offer potential explanations for certain puzzling phenomena observed in our universe. For example, the fine-tuning problem refers to the extraordinary precision of the physical constants that allow for the existence of life as we know it. The existence of multiple universes could account for this fine-tuning, as our universe might simply be one of the lucky few where conditions are just right for life to flourish. In this framework, life is not a rare anomaly, but rather a natural outcome of the vast array of possibilities present in the multiverse. As we delve deeper into the implications of parallel universes, we find ourselves at the crossroads of science and imagination. The multiverse theory challenges us to think beyond the confines of our observable reality, inviting us to explore the boundaries of what we consider possible. It fosters a sense of wonder and curiosity about the nature of existence, urging us to question the limitations of our understanding and the mysteries that may lie beyond. In popular culture, the concept of parallel universes has found its way into literature, film, and television, often depicted through fantastical scenarios and imaginative narratives. From science fiction classics to contemporary shows, the multiverse serves as a rich backdrop for exploring themes of identity, choice, and the nature of reality. These representations can inspire interest in the scientific foundations of the multiverse, prompting audiences to consider the real implications of these theories and their resonance with human experience. In summary, the exploration of parallel universes introduces a captivating dimension to our understanding of reality. The multiverse concept, stemming from quantum mechanics, cosmology, and string theory, posits the existence of countless universes, each with its own unique characteristics. Whether our universe is a singular bubble or part of a vast foam of realities, the implications of parallel universes provoke profound questions about existence, identity, and the nature of choice. As we continue to unravel the mysteries of the cosmos, the multiverse stands as a testament to the complexity and richness of the universe, inviting us to explore the depths of knowledge and imagination. The journey into the multiverse is not just an exploration of other realms. It is an invitation to understand ourselves and our place in the grand tapestry of existence. Well, if you're loving the video, give us a like and hit that subscribe button. The role of dark energy in expansion. The role of dark energy in the expansion of the universe is one of the most perplexing and intriguing aspects of modern cosmology. This mysterious force, which is believed to constitute about 70% of the total energy content of the universe, plays a pivotal role in the accelerating expansion we observe today. The existence of dark energy challenges our understanding of physics, prompting scientists to explore its nature and implications for the cosmos. To understand dark energy, we must first revisit the history of the universe's expansion. The Big Bang, which occurred approximately 13.8 billion years ago, marked the beginning of the universe and initiated its expansion. Initially, this expansion was decelerating due to the gravitational attraction of matter within the universe. However, observations made in the late 1990s revealed a surprising twist. Rather than slowing down, the expansion of the universe is accelerating. This discovery was unexpected and has led to the formulation of dark energy as a concept to explain this phenomenon. The evidence for dark energy comes primarily from two key observations: the cosmic microwave background radiation and the behavior of distant supernovae. The cosmic microwave background is the afterglow of the Big Bang, a faint radiation that fills the universe. Measurements of this radiation have provided insights into the overall geometry and composition of the universe. It suggests that the universe is flat and that a significant portion of its energy density must be attributed to dark energy. The second major line of evidence comes from the study of Type 1a supernovae, which are stellar explosions that serve as standard candles for measuring astronomical distances. In the late 1990s, two independent teams of astronomers observed that distant supernovae were dimmer than expected. This dimming indicated that they were farther away than they would be if the universe's expansion were slowing down. Instead, the data suggested that the universe was expanding at an accelerating rate, providing strong evidence for the presence of dark energy. So what exactly is dark energy? Despite its significant contribution to the dynamics of the universe, its nature remains one of the greatest mysteries in cosmology. Several theories have been proposed to explain dark energy, each with its own implications. One possibility is that dark energy is a cosmological constant, a concept first introduced by Albert Einstein in his equations of general relativity. Einstein initially proposed the cosmological constant to maintain a static universe, as the prevailing belief at the time was that the universe was unchanging. However, when it was discovered that the universe was expanding, Einstein discarded this idea, referring to it as his greatest blunder. In the context of dark energy, the cosmological constant represents a uniform energy density that fills space homogeneously, exerting a repulsive gravitational effect that drives the acceleration of the universe's expansion. Another perspective suggests that dark energy may be a dynamic field, often referred to as quintessence. In this model, dark energy is not a constant but varies over time and space. Unlike the cosmological constant, which remains fixed, quintessence could evolve, leading to different rates of expansion at different times in the universe's history. This idea opens up possibilities for varying properties of dark energy, but it also adds layers of complexity to our understanding of cosmic dynamics. Some theories even propose that dark energy could arise from modifications to general relativity at large scales. These theories suggest that our understanding of gravity might need to be adjusted when considering the vast distances involved in cosmological observations. If this is the case, dark energy could be an artifact of our current gravitational models rather than a distinct force or energy field. While dark energy remains elusive, its influence on the universe's structure and fate is profound. As it continues to drive the acceleration of expansion, scientists ponder the long-term implications for the cosmos. If dark energy persists, it could lead to a scenario known as the Big Freeze, in which galaxies drift apart over vast distances, and the universe becomes increasingly cold and empty. Eventually, stars will exhaust their nuclear fuel, and galaxies will become dark and silent, leaving behind a nearly desolate expanse of space. Alternatively, if dark energy were to change or dissipate over time, different fates could await the universe. Some models propose scenarios in which gravitational forces could dominate once again, potentially leading to a big crunch, where the universe collapses back into a singularity. Others suggest the possibility of a big rip, where the expansion accelerates to the point that galaxies, stars, and even atoms are torn apart. The study of dark energy has significant implications not only for cosmology, but also for fundamental physics. It raises questions about the nature of energy and gravity, as well as the validity of our current models of the universe. Understanding dark energy could lead to new insights into the fabric of space-time and the underlying mechanisms that govern the cosmos. As scientists continue to explore the mysteries of dark energy, they employ a range of observational techniques and theoretical models to deepen our understanding. Projects like the Dark Energy Survey and the Euclid Space Telescope aim to map the distribution of galaxies and the large-scale structure of the universe to gain insights into dark energy's properties. These endeavors seek to answer critical questions. Is dark energy truly a cosmological constant, or does it have a more complex nature? Does its influence change over time, or is it a fixed quantity? In addition to observational studies, researchers are also investigating the implications of dark energy for the fundamental principles of physics. Theories that bridge quantum mechanics and general relativity may hold the key to unlocking the nature of dark energy. For instance, exploring the relationship between dark energy and quantum fluctuations could reveal new dimensions of reality, shedding light on the fundamental fabric of the universe. As we navigate the intricacies of dark energy, we are reminded that the universe is a dynamic and ever-evolving entity. The interplay between dark energy and the expansion of the universe is a testament to the complexities of cosmic evolution. Our quest for understanding is not just an academic pursuit. It is a journey that invites us to explore the fundamental nature of reality and our place within it. In conclusion, dark energy plays a central role in the accelerating expansion of the universe, comprising a significant portion of its total energy content. While its precise nature remains enigmatic, theories ranging from the cosmological constant to dynamic fields like quintessence offer potential explanations. As scientists continue to investigate the implications of dark energy, we are challenged to expand our understanding of the cosmos and the fundamental forces that shape it. The exploration of dark energy invites us to ponder the mysteries of existence and the intricate web of connections that underlie the universe, highlighting the importance of curiosity and inquiry in our pursuit of knowledge. As we delve deeper into the cosmos, dark energy stands as a powerful reminder of the complexity and wonder that lie beyond our immediate understanding. Beyond the observable horizon, the concept of the observable universe and the implications of being beyond the observable horizon is a profound topic that dives deep into the nature of space, time, and the limits of our understanding of the cosmos. As we explore this vast expanse, we find ourselves grappling with questions about the nature of reality, the structure of the universe, and what it means to observe and understand the cosmos. At the core of this discussion is the understanding that the universe is not static, but is continually expanding. This expansion means that galaxies are moving away from us, and the farther they are, the faster they recede. This phenomenon is a direct consequence of the Big Bang, which set everything in motion approximately 13.8 billion years ago. Over time, as the universe has expanded, it has stretched the fabric of space itself, causing galaxies to drift apart. This leads us to a crucial point. The speed at which galaxies are receding can exceed the speed of light. According to the principles of general relativity, nothing can travel through space faster than light. But the expansion of space itself can cause distant galaxies to appear to move away from us at speeds greater than light. This can seem counterintuitive, but it is important to understand that it is not the galaxies themselves moving through space. Rather, it is the space between us and those galaxies that is expanding. The concept of the observable universe is fundamentally linked to this expansion. The observable universe is defined as the region of space from which light has had time to reach us since the Big Bang. Because the universe has been expanding, the observable universe is not a perfect sphere centered on Earth. Instead, it is shaped by the history of light travel and the expansion of space. Light travels at a finite speed, approximately 299,192 kilometers per second, or about 186,282 miles per second. This finite speed means that when we observe distant galaxies, we are not seeing them as they are right now, but as they were when the light we see left them. For example, when we observe a galaxy that is 10 billion light-years away, we are seeing it as it was 10 billion years ago, not as it exists today. This distance creates a kind of time capsule effect, allowing us to peer back into the early history of the universe. However, as galaxies move farther away, their light is not only delayed by distance, but is also stretched due to the expansion of space. This stretching of light causes a phenomenon known as redshift, where the light from distant galaxies shifts to longer, redder wavelengths. The greater the distance to a galaxy, the more pronounced this redshift becomes. This redshift is a key indicator for astronomers to determine how fast a galaxy is receding from us, and thus the rate of expansion of the universe. Now, when we speak of the observable horizon, we refer to the limit of our observable universe, the point beyond which light has not had time to reach us since the beginning of the universe. Currently, this horizon is estimated to be about 46.5 billion light-years away in every direction. This means that while we can see light from galaxies that are 46.5 billion light-years away, there are regions of the universe beyond this horizon from which no light can ever reach us. As time progresses and the universe continues to expand, more galaxies will cross this observable horizon, drifting beyond our ability to observe them. This phenomenon has significant implications for the future of our understanding of the cosmos. Eventually, as the expansion accelerates, it is anticipated that the observable universe will become increasingly sparse. Over immense timescales, on the order of tens of billions to hundreds of billions of years, only a handful of galaxies, particularly those within our local group, may remain within our observable range. This prospect raises intriguing questions about the nature of existence and observation. If vast regions of the universe are forever beyond our reach, what does it mean to understand the universe as a whole? Can we truly claim to have a comprehensive knowledge of the cosmos if large portions remain permanently out of view? These philosophical inquiries underscore the limitations of human perception and the tools we use to observe the universe. Furthermore, the idea of galaxies moving beyond our observable horizon leads to thoughts about the fate of the universe itself. The future will see an increasing isolation of our galaxy and a few neighboring galaxies as the vast majority of the universe's contents drift out of sight. This eventual reality may lead to a universe that appears eerily empty, where only a sparse collection of galaxies remains visible against the dark backdrop of space. The implications of this transformation provoke thoughts about cosmic loneliness and the nature of existence in a universe that is, on a large scale, fundamentally inaccessible. The concept of being beyond the observable horizon also raises questions about what lies beyond. If our observable universe is just a small bubble in a vast expanse of unobservable space, what might that space contain? Could there be other galaxies, structures, or even other forms of life? While we cannot observe these distant regions, they are still an integral part of the universe's fabric, existing independently of our ability to see them. This distinction between the observable and the unobservable leads to a rich tapestry of speculation about the nature of reality itself. As we navigate this vast cosmos, it is important to recognize that our understanding is continually evolving. Advances in technology, such as powerful telescopes and new observational techniques, may enhance our ability to probe the universe further, allowing us to gather data and expand our comprehension of the cosmos. However, certain limits may remain, dictated by the fundamental laws of physics and the nature of the universe itself. This exploration into the nature of our universe also highlights the interconnectedness of various scientific disciplines, such as astronomy, cosmology, and physics. Each field contributes insights that shape our understanding of the universe's expansion and its implications. By bridging these disciplines, scientists continue to unravel the complexities of the cosmos, seeking to understand not just what we can see, but also the mysteries that lie beyond our observable horizon. In summary, the concept of being beyond the observable horizon is a crucial aspect of our understanding of the universe. The continuous expansion of space means that many galaxies are receding beyond our ability to observe them, leading to a future where only a few nearby galaxies will remain within our sight. This phenomenon raises profound questions about the nature of reality, the limits of human observation, and the philosophical implications of an ever-expanding universe. As we continue to explore the cosmos, we must grapple with the idea that much of it remains beyond our reach, prompting us to reconsider our place within the grand scheme of existence. The journey into the cosmos is not just a quest for knowledge. It is an invitation to ponder the mysteries of the universe and the nature of our understanding within it. So, we've talked about infinite space, cosmic inflation, dark energy, and even the multiverse, and much more. But we're still left with that haunting question. If space is it expanding into something we just can't comprehend? One possibility is that space-time, the fabric of our universe, is the entirety of existence. There is nothing beyond it. In this view, space doesn't expand into anything because outside the universe has no meaning. Space itself, along with time, is all there is. Yet another possibility is even stranger. Some physicists believe that at the quantum level, space might be constantly fluctuating, creating tiny bubbles of space-time in a process known as quantum foam. Could it be that the universe's expansion is somehow linked to this quantum process, endlessly creating new space as it expands? The question of what the universe is expanding into has no easy answer, but here's what we know. The universe is stretching out in every direction, with no end in sight. It may have no edge, and it may not be expanding into anything we can understand. The universe just is. And as it expands, it reveals more mysteries that challenge everything we thought we knew about reality. For now, this mystery remains unsolved, a cosmic enigma that reminds us of how much we have yet to learn. Want to explore more mysteries of the cosmos? If you're fascinated by the secrets of the universe and eager to uncover what lies beyond the stars, we invite you to join us on this incredible journey. Subscribe now and keep your curiosity alive as we dive deeper into the unknown.